question, you can use your mic. If you're not able to, as usual, andika tu hapo kwa chat. What's it called? I'll inform the person presenting if it's need presentation. Haya, sawa. Andrew, unaweza anza.
Thank you. So, ladies and gentlemen, in front of you is Andrew Njoroge, ready to present a question entitled 1. Thank you. 1A. The question reads, the network of figure Q1, okay, I don't know if you can see that, I love to share. I don't have the paper where I'm sharing, but I hope you all have the papers where you are. So anyway, question Q1 has a circuit, and we're also given a pole zero plot. So we are told the expected form of the transfer function from the pole zero plot. So therefore, no, I'm not sorry. We are here. Yes. So this is the circuit, and this is a pole zero plot. Now, from the pole zero plot, we see there are 2 x's and 1 0. Oh, okay, x's as in the thing that marks the there are 2 at -1. If you go j up and -j down, there are 2 x's. Those are the symbols for the poles. Then at point 0 0, there is there is a circle at point 0 0. So that marks the 0. So therefore, we all know when you have a transfer function is the ratio of output to input. So normally in S domain, yes, but now when you have a transfer function, when the denominator goes to 0, that's where you mark the poles, and when the numerator goes to 0, that's where you mark the zeros. So here the x's mark the poles, and you can see it's at -1, -j, -1 plus j, and -1, -j. Now, as we do that, or as we see that, when you have a quadratic equation and then you solve it, it gives you the roots. So these poles, we took them as the roots to a quadratic equation, and therefore we worked backwards to find the quadratic equation, which is what you can see down here for the poles. So we just found the denominator first. So yeah, I think mpaka hapo tuko sawa. So the denominator we found as s squared plus 2s plus 2. Now the 0 is 0. So therefore it's not s plus something, it's just s. Now why we picked s squared, I'm not so sure, but I believe it's because number one, we can't pick s because the I have a feeling that the power of the top of the numerator should be equal to the power of the denominator. At least that's how it goes, especially since we are generating this for ourselves. So after all that, we found that the transfer function is s squared plus is this whole thing on your screens. Now, part B asks, let me see. Part B asks the actual transfer function, a quotient of polynomials in S involving RLC. Now, part B, you'd have to use the you'd have to use the circuit. So in this circuit, as you can see, there's one node at V1, and there's always a reference node somewhere. So the reference node, okay, it's not in the diagram, but we put it right below there, where the 0 would be. Right, that line of LS or SL, yeah, that's where the reference node hapo mwisho penye kuna branch. Yes, so for the node, you take this one up. You take V1 as seen, V1 minus Vs over 1 over SC, that is the current passing through that branch, plus the current passing through the LS branch, plus the current passing through the R branch, which is V1 over R. And you equate all that to 0. Yeah, so after that, some mathematics are seen there. We also see more mathematics down there. I'm just saying more mathematics because I hope what is a V2 on my diagram? Oh, the V2, if you look at the diagram in the V2 is the voltage drop. Okay. The voltage drop at the resistor, because that's what we were told in the question to consider as our output voltage. Where is it? Yes, Q1 is the output as a voltage across the resistor. So V2 is our voltage across the resistor. So basically it's also a V out. Yes, so there's more math there. I hope you've seen V1 SC plus 1 over LS plus 1 over R. Yeah, and all that jazz. Where else do we go? Yeah. So after this here, we have V1. Oh.
R1 V.
Wait, what's that?
Why have you used R1 V V1 V1?
R1 over V1.
V2 is V1 because it's the node voltage and we only have one node.
Oh, okay. Thank you, Gennaro. I was already sweating. Anyway, where are we? Yes. So after we are done here, we go to H of S, which is the transfer function. Now, as I was saying, we have expressed V1 in terms of Vs. Now the H of S is V1 over Vs, which is our wait. Yes, V1 is our output is our output voltage. So V1 over V now, okay, sorry. Here we have expressed our V1 over V1 in terms of Vs. Then here we interchange the V1 over Vs from here. We did cross multiply. Yes, we did the mathematics. I don't know what to call this, but that's where you go next after V1 over Vs. And then after that, we came here and simplified. This S over S plus 1 over LSC plus 1 over RC is a simplification of this. And finally, we came down here, where h of s is s squared over s squared plus 1 over LC plus s over RC. Yeah, and that was our transfer function. So the next question goes, the appropriate values of L and C for the given pole zero plot. So we have two transfer functions, one from part A and one from part B. Now, for the values of L and C, we basically equated them. We said the HS from part 1 should be equal to the HS from part 2. Yeah, and that's, so this is the H of S. And this is from part 2. And yeah, finally we get to the answer. We basically equated them where they were matching. So you see, like S over RC is equals to 2S, and 1 over LC is equals to 2. Yeah. And we found the capacitance as half a farad and the inductance as 1 Henry. So are there any queries thus far? Yeah. So sketch. Oh, sorry. The next question. The next question is part D. And sketch the frequency characteristics of the filter HJW versus W. So yeah, so HJW is basically HS. When you replace the S with the JW, it becomes HJW. But no, actually, it's a HS expressed in terms of frequency. So therefore, HJW is all of these. Okay, there was a lot of we had different methods, but it came back to the same answer. Personally, I just replaced S with JW from the H of S up there, and yeah, it comes down to this. Where is the equation? Here. Here. Yes. So now to get HJW magnitude, you do the square root, then you do the square, then the square root. The magnitude is the square, then the square root of the thing you're trying to magnitude. So now HJW squared is equals to all that squared, which then translates to all that. So I hope you've seen where this has come from. You basically square the JW, what is it called, the equation you found up there. Then you end up with something like this. Yeah. Okay. So then, after ending up with something like that, you then come and put it under the square root. And after that, you simplify. You simplify. You simplify and you get there. And after simplifying and getting there, you finally get here. This is supposed to have a square root over 1 plus 4 over W4. Yeah, there's supposed to be a square root there. Sorry, it's missing. The denominator is supposed to have a square root. Ah, yeah. Are we okay up to there? So, okay, now how do we sketch? After getting this, see, this is the HJ, this is the HJW in reference to W which is the frequency. So now you plot the values of W and the values of HJW. So for every value, of W that you pick arbitrary values, then for every value of W that you plot, you put it in the equation, and after putting it in the equation, you come up with a sketch for your plot. Yeah, so the maximum frequent, it's what can I say? It's heading towards 1, but it's not really touching 1. If you do this mathematics, you'll see as it goes to infinity, it's not touching 1, but it's just about there, 0.99, going there, going there, going there. Yeah, so yeah, I guess that's it. Are there questions? Okay. So we determined that this is a high pass filter because this curve is from the places we researched. This curve is synonymous to high pass filters, and also you can see it's killing the as you go. It's killing the voltages as you go towards 1. As you go towards 1, it's killing off the HJW, but as you increase towards 4, it's allowing the HJW to pass. So that's what a high pass filter does. It kills off the low frequency values. What else? Yeah. Now we are on part F, if I'm not wrong. The type of filter, we have already answered that. Part F states the cutoff frequencies of the filter. So if I zoom out a bit. Cutoff frequency has always been given by one thing. So we know W is equals to 1 over the root of LC. But W is equals to 2 pi F. So therefore, F is equals to 1 over 2 pi LC. So yeah, and L we had 1, C we had half. So basically, this is what is being done over here. Sorry for the handwriting, but in the what we'll send to the group, it will have better handwriting. So yes, but basically that's the logic, and we ended up with 0.2250 hertz. Yeah, so now we are in part G. Part G. Part G states the Z parameters. Oh, okay. So for the Z parameters, we did loops. What? This was it. Wait, actually, ngoja kidogo. Sorry. Iko. Sawa. Sorry. Yes, as I was saying, for the Z parameters, we did loops and KVL. So I1, I2 at the end, I3 in the middle. So then we expressed hapa. We expressed it here. The different with the three loop equations, if I may call them that. Yoyote. Then we expressed I3. We took the last 0 is equals to I3 and all that. Then we expressed I3 in terms of I2 and I1. That's what's down here. Yes, so after we did that, now after you do that, where there is I3 in V1 and V2, you'll replace with the expression for I3 that you got. So like V2, V2 tuliingiza hapo kwa V2 is I2R plus I3R, then tukaingiza for the I3, as you see, we replaced, yes, and came up with our equation for V2. And we also, likewise, we came up with our equation for V1. V1 was I1 plus, yes, all that uko juu. Then we came up with our equation for, what is that V1 hapa? V1 ilikuja ikakuwa hii. Yeah, and after getting V1 and V2 in terms of I1 and I2, we all know that Z11 is V1 over I1 when I2 is equals to 0. So therefore, with our expression of V1 and our expression of V1 had when I2 goes to 0, yeah, yes. When I2 goes to 0, all this goes to 0. All the e part yote ya I2 will go to 0. Then, so you remain with this I1. So V1 over I1, the I1 will cancel. Then you are remaining with the thing inside the brackets of I1. So that's what you have done down here. And then you replace the values. We have C, we have L, we have R. So then you replace the values with the values you got earlier. And finally, you end up with such. Yes. Yeah. So, and that's the same procedure for the rest, for Z12, for Z22, and for Z2. You just where I1 is equals to 0, you take that whole expression to 0, yeah, and you divide, then you substitute the values and get your answers. So ndio hiyo yote, yeah. So part H, um, part H was you're supposed now to write the question was the driving point impedance of the network and sketch its pole. Oh no, oh yeah, and sketch its pole zero plot. Can I do the star delta conversion thing here? Ooh, no, personally I can't. I don't know if there's anyone, if there's someone. Michael has a question. Anyway, so part H, there was, the question was about, so now when you see the, what is it called? The driving point. So the driving point impedance is the impedance when no source is attached. When no source is attached, if I'm not wrong. Yes. It's basically the impedance of the circuit, which where all the components now part of the total impedance of the circuit. So in our circuit, when you start from the right, going to the left, when you're considering the circuit. So then our circuit, the L and the R are parallel to one another. Parallel, yes, to one another. Then the capacitor is in series with both of them. So therefore we took the parallel part, yes, calculated it. Then we added, it's the driving point impedance is the impedance when there is no source attached to the circuit. Yes. It's basically the impedance of the circuit when you consider all the components without the source. So, where was I? Oh yeah. So yeah. So the capacitor you add to the parallel part. Then after that you do mathematics. This is the when you replace what is it called? When you I don't know what what is it called? Ushikanisha hapo chini, then una divide by one of them.
Mr. Andrew.
Okay, so yes, this is you do all this. I've seen your question, Joseph. I'm coming. Then you substitute the values. You substitute the values hapo. Yeah. And then finally you end up with this. So now to Joseph's question, what is so that my definition is not clear. So what's my definition of what's the driving point impedance? The driving point impedance is the impedance of the circuit when you take away the source voltage or the current source or the voltage source. Yes, that's all. Okay, so after getting the this is now this is the D of S. This is the D of S. Okay. Now we are supposed to draw our own pole zero plot. So how do we do that? As I said, poles are when the denominator goes to 0 and zeros are when the numerator goes to 0. So you equate the numerator to 0. You find the root. Yes, then you find the roots. And if you notice, our numerator is what was our denominator in part A, and our denominator is what was our numerator. Oh no, wait. No, yes, no, the numerator is the denominator is different, but our numerator now is what was our denominator in part A. So then the roots will remain the same. So when the roots remain the same there, our poles now will be s squared plus s is equals to 0. So our poles, you get it here. So these are our poles, and this is our zeros. Yeah, so now the whole plot comes to be this beautiful photo over here. Are we okay up to there? Because yeah, I think I'm done. We are done. Yes, thank you for your time.
There's something I'd also like to add on the filter part. From our calculations using the transfer function, we got, because the filter was composed of two components, the inductor and the capacitor. So there were two parts to that graph. The first part, which is like slanting down kidogo, alafu the other part is down, which is going towards infinity. The first part was due to the inductor and the capacitor, because most inductors will act as a low pass filter. So this was like an inverted low pass filter because of where we placed our inductor. Alafu the other part, which heads towards infinity, was due to the capacitor. So in this type of that circuit would have given a sort of an inverted band pass filter, according to the research I did. So that's what I wanted to add.
Thank you, Gennaro. On to number 2.
Oh, okay. Thank you, Gennaro and Njoroge.
But the term inverted bandpass filter, I don't think it's an agreed upon word. So so don't write that in exam. But I'm saying how it works. It works how a bandpass filter would work, but invertedly. Instead of taking the frequencies between 2 points, the way a bandpass filter only takes frequencies between 2 points, two allows frequencies between 2 points to pass. So in this case, it will allow frequencies below a certain point due to the inductor part, and frequencies above a certain point towards infinity due to the capacitor part. So yeah, that name inverted, I don't think it's agreed upon, but just for understanding, you can just say it's an inverted bandpass filter. Yes.
I think next was Gisheru. Gisheru, right?
The next question. Please, Travis, please go first with the Smith chart.
I was to do question 2, part B, but I'll take a different approach where I'll sort of take you through the Smith chart and then come back to that question a bit later. So this is, I sort of drew this to start like for people to get how a Smith chart looks like. It's basically a set of circles that their edge at one point and a set of arcs that also originate from the same point, going sort of flattening out. So even this straight line in the middle is an arc per se. And so the circles denote the resistive part, and then the arcs denote the imaginary part when you're given an impedance, to say. Yeah, so that's how it looks like. So this is the Smith chart itself. As you can see, like so it's explained the same. The circles here, like the resistance and conductance components, that's the R and G. And then towards the top half of the circle, either your inductive plus J or your susceptive plus J, and then the bottom part are the negative of the same. So for the first part of Smith chart, usually given you're given a ZL, and you'll also be given Z0. The Z0 is your characteristic impedance, and your ZL will be your maybe your load line or your source impedance. Like okay, words imepotea, but it's what Nani was explaining, Andrew, the source impedance, kituka hiyo. Like the impedance you see when you're at the source. Yeah, that's your Z capital L. So the first thing with your Smith chart, you take your Z capital L and you divide it. So ZL over Z0, you get Z cap small l this time. And you do this because for most Smith charts, you'll have a normalized one. And the normalized means that the middle point here, it's at 1.0. And a normalized one will have maybe a 50 ohm there, 100, something like that. But the lecturer said he'll always use a normalized one. Yeah. So we can take maybe, I'll use an example where our ZL is 35 plus J 60, and our Z naught will be 50 ohm. So if you do this by this, you'll get a small ZL as 0.7 plus J 1.2. So this is what you're going to plot inside your Smith chart. So the 0.7 is the resistive part. So you come to this straight line here, and you look for the circle with 0.7, basically. So it's, okay, that's not straight. Yeah, but basically, yeah, that full circle around 0.7, and then plus J 1.2, you come to your arcs over here, and 1.2 is at this point. Our 0.7 was here. So you look at where these two lines meet, from the 0.7 and the 1.2, around there. And then after that, you draw your constant VSW circle, VSWR, I believe. This is my pair of compasses. Put your point at the middle, 1.0, and extend the radius up to that intersection point. And yeah, and now you draw your circle. Yeah, so this is your constant VSWR circle. And the first question, okay, for most questions, you'll be asked, you find the VSWR, which is voltage standing wave ratio. And you should note that this is always greater than 1. So you'll come to the right side of your Smith chart, and that's where you'll take your reading of VSWR. And for this one, I did it early. It was around 3.9 or so. So that's the first thing you'll be asked. And then the next thing will be to find voltage reflection coefficient, which is this thing. This thing now. So for that, you take your radius of your constant circle, you can pick it, and then come read off from the Blackmagic Smith chart. It's the very last scale down here. So you pick this radius, and that radius you read your, yeah, you read off the scale whatever it will give you. So for this one it was 0.6. Oh, I can't. This is the same. Yeah, just about 0.6 or so. And then this ratio, okay, so you have that the first part is a 0.6, and it also has an angle. So for this angle, usually you draw a line straight from the 1.0 through your intersection point, and you make sure it extends beyond. So something like that. And then you draw a line, and these scales out here, the very out one, the farthest outside is wavelength to the generator. The next one is wavelength to the load. And then the next one now is one you're going to use for this. It's, if you have a limit that you can read from here, this side here, it's angle of reflection coefficient degrees. So that's your angle part here, which is 0.69. Nice. That's a 9. Believe it, only 9. Yeah, so basically these are the things you'll be asked, and also since this is your ZL line, you can be asked like, what is the impedance at 0.1 meaning wavelength from this line, from your load line. So for that, you just depending on whether you're told either to the generator or from the generator, you add or subtract from this point, from the center again, draw the line, and you read. At this point, you read the full circle here. For this one is about 1.4, and then the arc line going up J 1.7 or something. Yeah, so that's basically how to go about it. And I think you can also be given this voltage reflection coefficient to go back to and find your ZL. So is that you come measure 0.6, that's your radius, draw your circle, at your angle you're given, draw a line, draw a circle, and this point will be your ZL. So it's just manipulating that and that, yeah. So the next part is matching, sub matching. It's a match. So assuming this is your transmission line and you have your load here. So a stub is basically introducing like another line parallel to your load to I don't know if it's to remove the reactive part so that you just have the resistance, or to remove the resistance to just have the reactive part. I think I didn't read that part well, but if anyone knows why we match stub, they can they can chime in anytime. But I think I know how to do it. So since we are now introducing this as tab with its own load here, when using the Smith chart, we basically want to find out this distance here. We can call it L1. We want to find this distance. Okay, the distance from the load to where your stub will be. Distance from where the stub will be to where your, your distance here, we need to find it, L2, and we need to find the admittance of your stub. And in stubs, we use admittance and not, impedance. Yeah, we use admittance, not impedance. So it will be the same as before. You'll be given a ZL. This is your ZL. So like before, you get the normalized one, the small ZL, and then you come to your Smith chart, you plot the resistive and the reactive part. You find that intersection, bring your compasses. Yeah, do that. You draw your ZL line, but this, let me draw it and then I'll explain. You draw up here will be a ZL, and since you are going to a straight line through our ZL point up to the other side, which will now become our line admittance. So for matching, see this our constant VSWR circle, we are going to look at its intersection point with software. Snip and Sketch. It's just on Windows, I think. Yeah, you can import images and just draw. You can enough tools. Found it better than using Paint 3D. Yeah. So saying you look for intersection point between your constant VSWR circle and this complete circle where R, or rather G in this case, is equals to 1. So let me highlight it. Yeah, so this is your G is equals to 1. So you're going to look at this intersection point here and this one here, but you can choose any that you want, but I'll go with this one down here. And so the objective now is to draw a line from the middle point through this intersection point. Yeah, so you draw that line, and this will be your stub position. This here, L1. This will be the admittance of your stub. So to read its value again, you know it's a 1, because its G is L1 is equals to 1 minus, because it's on the lower half of our chart, minus 1.4, I believe, minus J 1.4. So that's the first thing. And again, you can get this distance between the two of them, and this will be this distance here, your L1. So you just read, you can use either, you can use either of them, because you're just finding the difference between these 2 points in terms of wavelength, say that to generate or to load. And yeah. So towards the generator, this is 0.36, 0.326 minus 0.389 or something. 89, and you get that. Yeah. So the next thing will be left to find is this distance from where the stub will start to the actual stub itself. So for that, negative value, for this one, the correct value will be 0.38 minus 0.326, so actually, it's not negative distance per se. Yeah, so we just do the larger one minus the smaller one for simplicity's sake. So if you do this, just eliminate the negative while you're done. So to find this distance here, we have our stub being 1 minus J 1.4.
Oh, done.
But
Sorry to
yes,
interrupt you. There's a question. Situna is asking, can you do towards the load or towards the generator is recommended?
You can use any of them. Like I said, it's just the distance between the two of them. So both should ideally give you the same difference between the two. I don't know if I make sense. Because some hapa ni 3, hapa ni 5, and maybe another scale says this 6 and 8. Ideally, the difference between these 2 points should still be the same. I haven't tried, but yeah, I think it should be the same, so you don't have to worry about that. Let me take you people behind kiasi. When I said our example here, 1 minus J1.4 is admittance of the stub. I think you can confuse kiasi. That value is the admittance when you look at this point, like at where the stub will be. That will be, this is the value tumepata hapa. That was the intersection point between our G is equals to 1 and our constant VSWR circle. Yeah, that's that. And then now for the stub, for the stub, we usually want to, like we want a value that will sort of eliminate the admittance that you're looking at that point. So since we have a negative J1.4, we're going to, our stub will be the positive value of that. And the resistive part is a 0. So if you have like a plus JB, your stub susceptance will be negative JB. Yeah. So for ours was negative 1.4. So we're going to take positive 1.4, which is here. And for this now, we draw a line straight from the center of it through our J 1.4. We are picking it at the edge because remember, the resistive part was a 0. The largest circle here is 0. Yeah, so it's 0 plus J 1.4. Which is now that line. This is our stub line. There, it's admittance. So for this del, so we are looking for this distance here between where, this was our load. This is where the stub will start, and here is where the stub will be. So we just look for the distance between here and that part. Again, you can use either to the load or to the generator. Oh, no. For this one, we're going to use to the load, because it's from here, this is, the stub is sort of like a load. So from here to the load, and you read your lambda there, and yeah, calculate like the difference. Double stub, I think. For double stub, it's sort of the same as this one, where we use this r is equals to 1, but then you translate it back. I think, let me try and do the question now. Ndio nisiwachanganye sana with too much. So you're being asked using a Smith chart on a 100 ohm transmission line. This is a characteristic impedance. Match the line to the load. ZL is equals to 70 plus J50. Yeah. So it's 70 plus J50. This is our Z capital L. We divide this by our Z naught, which was 100. Z naught, we get 0.7 plus 0 plus J 0.5.
Oh wait, Dan.
Yeah.
It's 70 minus J50.
Oh, it's minus. Oh.
Sorry.
Oh, thank you. So minus. Again, see, you know the drill now. 70 is the resistive part. So you come for the 0.7 circle. That one. And J 0.5 should be somewhere here. And you look for the intersection points. I think there. And draw the circle. And at this point, you can also draw the ZL line so that you can get the admittance also. Yeah, so kuchini ZL, and then completely opposite will be YL. Yeah, so match it using a single stub. Like I said, now we take our this complete circle where R is equals to 1.
Then,
Yeah.
pole sana kidogo. Do you have to draw the circle on the right side?
No, I'm just drawing it so that you people can see it well. But
Or
Like it's already there, so you don't have to draw it again.
No, but usually, like if you're told to draw, can you draw it almost on the left, on the no, on the wait, it's on the right, it's on the right side. Yes. Can you draw it on the left side?
This, the one r is equals
Yeah.
to 1?
Yes.
And no, because
Okay.
see, like the chart is like this.
Mm-hmm.
See, it's that, okay. Yeah, but the smallest one, like numbers in is 0, 0.51, 1.5. So this is a complete circle in itself. You can't always move, like we're taking the circle where r is equals to 1, or rather g is equals to 1. So we can't shift it.
Oh.
The only time you can rotate it is in the double stub matching.
Oh, okay, so thanks.
But for single stub, yeah, unatumia tu paliko.
Sawa.
Yeah. So again, we have our YL. We take the intersection point between our the constant circle, VSWR circle, and the then where G is equals to 1. That intersection point, you draw another line. So okay, this is a YL1. Like if you remember that diagram, this is ZL. ZL, a start tuseme itakuwa hapo. So our while L1 is the admittance at this point. So the difference between this and, okay, this one I should use Y, don't confuse it, yeah. The difference in wavelength between these two is this distance here. Yeah, so we just pick okay, I can't see why I did it, but yeah, basically you pick this minus this. If either to the generator or to the load. Again, I don't think it will matter that much. For this one, it's about 0.152 or something, and 0.1444 or 45 or there. Yeah, 45 we get 0.007. So 0.007 wavelengths between here and here. That's a distance. So the next part, we read off this point here to get like the actual value of this. So it will definitely be 1 because like in attach this G is equals to 1 circle, and then the angle here will be 0.7, 1 plus J 0.7. Yeah. So taking your 0.7 here, we know that our Y stub will be the negative reactive part of this because this one is positive. So Y stub will be negative J 0.7. Yeah, so here you go, right here. Again. So this is our Y stub. So giving its location, tumepata location 0.007. Its length yeah, but its location, I think it's the 1 plus j.7. Its length is this. And then you also asked for the termination. The termination distance now will be from your Y stub here up to this. Pulling. So at termination, instead of having like a whole component there, we can terminate it in a short circuit. Actually, I think Mekwan can mislead because a lot of them have been saying either short circuit, open circuit, but mostly short circuit. And if you come to Smith chart, on this end is your open circuit, and this other end is your short circuit. So find its termination. It's your Y stub here. Reading it towards the load. So the wavelength here up to the short circuit, which is 0.25. So 0.25 minus 0.996 or something of the sort. Yeah, so that will be your termination. Which is 0.154. This the distance to where your short circuit will be. And then the last one will like shortest distance from the load to the point where QWT may be used to match the same load. So remember, our load is here, and the entire circumference of the Smith chart is a half wave. So from 0 to 0.5. So a quarter wave will either land at 0 over here, or 0.25 over here. So the shortest distance is from, like, definitely it's to 0.25 minus 0.145 here. So that's our shortest distance. If our YL was somewhere there, shortest distance will be to the quarter wavelength will be to the 0.5 or to the 0 here. Yeah. But for this one, 0.25 minus 0.145 give you 0.105. Yeah. I think that was it with my question. Sijika bado mko au mmefloat kabisa. Yeah, that's it.
So, thank you so much, Dan.
Karibuni.
Gisharu, you can present.
Hello, hi everyone. So we'll be going through question number 3. I'll take us through part A, and then Fiona will take us through part B, and we did not go through part C because it is outside the scope of transmission lines. But we might cover it tomorrow, hopefully. We'll see. I'm assuming everyone has the question, so I'll just read it out. A 15-kilometer long transmission line operating at 1.5 kilohertz and terminated in its characteristic impedance has an output of 2 volts RMS, lagging by 150 degrees, for an input of 8 volts RMS. Determine the attenuation coefficient, the phase shift coefficient, the line wavelength, the line dielectric constant, and the line phase velocity. So first of all, let me present someone tell me when you can see my screen.
Yeah, we can see.
Okay, can see it. Okay. So first of all, are you guys all familiar with this equation? This first one. Like, are there any questions concerning it?
No question.
Which this is a general form.
Oh, you're being told
voltage
to
equation.
zoom in.
Is that fine? Is that better?
Yes.
Okay. So again, does anyone have any issue with this first equation?
Oh, someone has raised their hand. Oh, please could you explain?
This equation is a general form of the voltage equation for a transmission line. Let me just open up the text real quick. So if I can refer you guys to page 66 to 67 of the class notes. This thing, the whole thing is very, very long. So I wasn't very motivated to type all of it out since it's already here. So okay, I will just walk you through like everything. Let me try. So do you all have the diagram on the equivalent circuit of a transmission line? The the people who have 66. The equivalent circuit. Consider the currents and voltages in the transmission line equivalent circuit for a length delta x in figure 2.2. Okay, so when we're going through this model, we saw that in order to properly analyze it, we took okay, let me just read so that I don't confuse anybody. So in order to analyze this thing, the transmission line with its distributed circuits, can you call them like circuit parameters? They're all sort of lumped into what appears to be a T network or a pi network, depending on how you look at it, since it will have infinite length. So it will be like a cascade of T networks or a cascade of, could you share your screen? Okay. I'm using the hard copy notes. I'm using hard copy, but I think I have the yeah. Can you see that, Joseph?
Yes, you can see.
Okay. So is the equivalent circuit. We will start from down here. Since each conductor has a certain length and diameter, it will exhibit a resistance and an inductance. The closeness of the two current carrying conductors also ensures some capacitance. The imperfect dielectric used to separate the wires experiences current leakages equivalent to shunt conductance. Okay, from here, the model is thus given for transmission line length dx and all the parameter values expressed in terms of the length dx in figure 2.1 as cascade of such sections will end up be seen as either a cascade of symmetrical pi networks or symmetrical T networks, for which previous theory would then apply. So the complete transmission line is seen as a cascade at RF, since the capacitive susceptance is much larger than the conductance, and thus RG may be ignored. It's considered lossless. So these parameters R, L, G, and C are known as primary line constant, and they're constant because they do not vary with voltage and current. However, frequency dependent to some extent. So the units for the constants are series resistors, ohms per meter. Remember, everything in transmission lines will be in per unit length meters. Keep that in mind. Everything will be in per unit length. So it's ohms per meter. The series inductance is henries per meter. And remember this same units as permeability of a medium, mu is L. G, the shunt conductance, which is Mo, MHO. I don't know how to say that thing per meter, which is the same units as the conductivity, and shunt capacitance, which is the same as the permittivity. Yeah, these elements are shown lumped in the equivalent circuit, but in reality they're actually distributed, so they should not be assumed to be lumped. So the next section is on how frequency varies along the line. So due to the skin effect, you guys remember skin effect about how the faster the frequency, the more the current tends to concentrate at closer to the surface of a conductor as opposed to the middle. So due to the skin effect, current is more concentrated to the surface. The skin depth is given by delta is equal to 1 over the root of pi f mu sigma. And it's the depth of penetration at which the electric field decreases to about 36.8%, which is 1 over E. For open lines, L is almost constant, but for screened, it decreases with increasing frequency. C is virtually constant. G increases with increase with frequency due to the increasing the electric loss with increasing frequency. So yeah, this is the other part that this is where like that equation will come from. So the part I went through all of that before because of this dx part. I wanted you to see why dx comes in. So if you consider these, the change in voltage V1 to V2 is going to be given by delta V is equals to minus I Z dx. I'm not entirely sure why it's minus I, but I'm going to guess that it's because the line, the voltage will at the output will be less than at the input or something. I'm not entirely sure about why it's minus. If anyone knows why it could be minus, you can say so. But it also may be attributed to taking the current I2, like the current going out towards the output terminal is being considered to be moving in the opposite direction. So we'll take it as minus because ideally it's moving towards the left from our knowledge of two-port networks. So since it's going right, it'll be negative. It'll be minus I times the impedance being Z dx. And now ignoring this, what I've just said, delta I will be, well, the same. I think the negative will move to the other side. So delta will be equal to minus Vy delta x. So these will give us the equations dv is equals to that, which is equals to this, and di is equals to that, which is equals to this. These two equations with respect to x, where we take d over dx of uv, it's going to be equal to d. It's going to be equal to u dv over dx plus v du over dx. So here, this first term, you see we have minus iz. So the first term will be I dz over dx. The second term will be z di over dx. And they're both negative because it's negative. And then here we'll have minus I dz over dx plus, we know that di over dx is equals to minus vy. So if we plug in minus vy into minus z di over dx, we get positive z by v. And the same thing happens here. D squared over dx squared is equal to minus v dy over dx minus y dv over dx, which is equal to minus v dy over dx plus zy. But from what we read earlier, the uniform line, for uniform line, the values of the line constants do not change. So dz over dx change in z is equal to change in y, which is just equal to 0. So you end up with these equations. Okay, disclaimer, these equations 2.05a and 2.05 Roman 5b, I don't know where they came from. I don't know how they came into being, but to explain equations 2 Roman 4, equations 2 Roman 4, Roman 5. So like, okay, I'm sorry, I did not write this down, but I hope you guys will be able to follow.
Gishu,
Yes.
Hala, I think what we're looking at 2.04a and b is the solution to 2. Yeah, what we're looking at 2.5a and b is the solution to 2.4a and b. Those are like corresponding solutions. When you go back into the hardcore math and solve for them, their solutions nizo.
No, I'm saying I don't know the hardcore.
Oh, okay. Oh yeah. I'll
to know
yeah.
the hard.
Sorry?
Yeah, so I just took them
Oh
as
yeah,
is,
it's okay to consider them as a given.
because that's, yeah. So if you work from equations 2 point this upwards, if you do double differentiation, whatever, if you do that thing on these two equations, you're going to end on equations 2.05, you're going to end up with equations 2.4, because if you take, let's say, if you take v is equals to e power gamma x, if you do dv over dx, you're going to get gamma e gamma x. And if you do d squared v over dx squared, you're going to get gamma squared e gamma x. But we know from the next line that gamma is equals to the root of zy, and v itself is equals to e gamma x. So if you replace gamma squared with zy, and you replace e power gamma x with v, you're going to end up with d squared v over dx squared is equals to z by v. So something. So the coefficient gamma is called the propagation coefficient for the line, and may be expressed in terms of primary line constants as gamma is equals to the root of r plus j omega l into g plus j omega c, which is equals to alpha plus j beta. And I think this thing of alpha plus j beta is in 2-port networks, which will be covered tomorrow. Oh, okay, so we'll go to the next page. Where alpha is the attenuation coefficient, the units of NEPA per unit length, and we'll use SI units, so it will be NEPAs per meter, and beta is the phase shift coefficient with units of radians per unit length, radians per meter. So the general solution for the voltage, now this is what that equation is, the general solution for the voltage, which is V1 E power gamma x plus V2 E minus gamma x. So it will come later. If you include the time variation, we'll just multiply V, big V, by e j omega t, which introduces the whole thing of sines and cosines. Yeah, cosine of omega t plus j sine of omega t. So if we include that, we'll end up with v1 e. Okay, if we include ej omega t and then we expand gamma into alpha plus j beta, you're gonna get, we'll have v1 e alpha x plus j beta x plus v2 e minus alpha x minus j beta x. And then each of those will be multiplied by ej omega t. So, okay, it's a lot of just substitution and rearranging the equations and all that. It's not that complicated to move from here, to move from equation 2.2a to 2.2b. So I'll just move on from there. So the imaginary parts of v of x and t, which is depending on the form of the source. So if the source is given as a sine, you'll take the imaginary part. The voltage in 2.2 is seen to be composed of two waves traveling in opposite directions. And this you can tell from here. We look at the exponent. One of them has a negative, the other one does not have a negative sign. So one is moving in the positive x direction, the other one is moving in the minus x direction. That's the manifestation of the negative. As voltage magnitude reduces with distance traveled along the line, in the case of lossy lines, the second term represents the wave traveling in the positive x direction. The second term is going towards the load. That's what they mean. And the first term represents the wave traveling the negative x direction. So that one is moving from the load towards the source. So if we consider the forward traveling wave alone, which is the second term only, it's noted that minus alpha x provides the attenuation so that the voltage reduces with magnitude. The distance away from the source located at x is equals to 0. Okay. Well, omega t minus beta x provides the phase, which is noted to reduce as the distance from the source increases. Okay, so that is basically how that formula comes into play. I hope. Nimekula nyama sana. What does that mean? Okay. So does that answer the questions on what that formula is?
Yeah, I think we know where it comes from now.
Joseph.
That's a good place to work from. Thank you.
Right. So then shall go back to question. Sorry?
No, Katiko says more or less.
Okay, let me just open up. I'll press the question. Okay, so I think this equation, this is like the place to start when it comes to this topic, this unit. I think you need to properly understand this general voltage equation thing in order to move forward without any issues. So, the attenuation coefficient. So we've already come across the attenuation coefficient from that brief intro. So from two-port networks, if the line is terminated in its characteristic impedance, which it says so in the question, And that is why we will only be considering the forward traveling wave, which will have the negative in its exponential. So if the line is terminated in its cadence, n, which is attenuation, will be equal to the root of input 1 divided by the root of the powered port 2. This is again explained in two-port networks. And you get to attenuators and filters, which we know that power is equal to v squared over r. So it's equal to the root of v1 squared over the characteristic impedance z0 divided by the root of v2 squared over z0. The z0 will cancel, and the voltages will be rooted, so you'll get v1 over v2. But we also know that attenuation is equal to the source voltage, the voltage at the source, divided by the magnitude on the line. This formula. Any issues on this formula? I got it from the notes. Because this Vs is the voltage, is V1. And this is V2. You guys can see that?
Yes, no issues.
So writing Vs is just like writing Vs e power 0, because e to the power of 0 is just 1. So it's going to be Vs e power 0 divided by source voltage e to the power of minus alpha x. And we're taking alpha x because we're only taking magnitude of the voltage, we're not taking the phase shift. So beta is not going to be included here. We'll only take alpha x. So that will become 0 minus mego n. So the attenuation is just equal to e to the power of alpha x. So we are told in the question that V1 input voltage is just 8 VRMS, and the output voltage is 2 VRMS. The VRMS will cancel, 8 divided by 2 is 4. So n is equal to 4, and e power alpha x is also. So to find n in amperes per meter, first we need to do the natural log of this, because in amperes, this is e power alpha x. So to get in amperes, which is just alpha x, we need to find the natural log of 4 by, well, the per meter. So you'll end up getting natural log of 4 divided by 15,000. Because we're told that if you plug in 4 here, you're going to end up with 9.242 times 10 to the minus 5 amperes per meter. Log of the attenuation divided by the length. So it's 20 log 4 times 10 to the minus pulse per meter. Are we good until there? Any questions? Questions? So here, the phase shift coefficients. So here in the question, we're told that the output voltage lags the input voltage by 150 degrees, which is basically the phase shift. because the output wave has shifted in phase by 150 degrees relative to the input. So for this part, all you'll do is convert the phase, convert this lag thing to radians, and then make it per meter, because that's the unit in which the phase shift is given. So to convert an angle in degrees to an angle in radians, it's 2 pi times the angle divided by 360 degrees, or pi times the angle divided by 180. So if you do 2 pi times 150 divided by 360, and then divide that, all of that, by 15,000, you will get a beta, a phase shift coefficient of 1.745 times 10 to the minus 4 radians per meter. Questions? Are we good?
Yes.
So onto the line wavelength. So for beta is equals to 2 pi over lambda, I think I explained it a bit here. So we already know this form. We already went through that previously. So for constant phase on the line, we need this phase shift thing to be equivalent to 0. It says so. It says so. Where does it say so? Here. Here. In order to maintain constant phase on the line, omega t. This is supposed to be constant. Sorry, not constant, not 0. Omega t minus beta x equals to a constant, and when you differentiate a constant, it ends up being 0. Sorry, my mistake. Sorry about that. So this will be equal to this will not be equal to 0. This will be equal to a constant, and then when you differentiate all the terms here with respect to time, you end up with this omega dt minus beta dx over dt is equals to 0. Take beta dx over dt to the other side. Omega is equals to this, and then if you take beta to the left, you get dx over dt is equals to omega over beta, and we all recognize dx over dt as the rate of change of distance with time, which is just velocity. So therefore, the phase velocity of the wave becomes this omega over beta, and we know that the velocity of a wave is given by the wavelength times the frequency, lambda times f, and we know that omega is equal to 2 pi f. So therefore, if we substitute these in here, we're going to get lambda times frequency is equal to 2 pi f over beta. Making beta the subject of the equation, you're going to end up with that. Beta is equal to 2 pi over lambda. So that's where that equation comes from. So yeah, beta is equal to 2 pi over lambda. So you make lambda the subject, you get lambda is equal to 2 pi over beta. We have a value of 2 pi, the value of beta, 2 pi over beta. You get, okay, if you use the value of beta that is not, this has been rounded off, so your answer will be slightly off this. But if you just plug this into the calculate, if you plug this into your calc and then you put it here, you will get lambda is equals to 36 kilometers. Are we Good until there. Any questions?
No questions.
Question. Constant. So lambda is equals to the speed of light divided by the root of the permittivity, the relative permittivity of the dielectric, the transmission line's dielectric times the frequency of wave propagation. Again, I have it over here. So here, this thing, Vp is equals to 1 over the root of 1 over the permeability times the permittivity. This comes into being from Maxwell's equations, and I didn't go into that. I could not handle all of that. But somehow, if you go and analyze if you go look up anything to do with Maxwell's and this equation, you're going to find a good enough explanation, which I do not have right now. But for what's relevant to ECT, this is all you need to know. The velocity is equal to 1 over the root of mu epsilon. But you know that mu is equals to mu naught mu r, and here we're going to end up with 1 over that thing. And we know for free space, if you plug in free space values here, we're going to have Vp naught, which is equal to the speed of light, which is 1 over mu naught E naught, meters per second, meters per second, meters per second. So for common dielectrics, mu r will be equal to 1 out 1 over mu naught E naught over the root of mu naught E naught from here, and then you replace it with C, because C is this, you're going to end up with Vp is equal to C over the root of the relative permittivity of the dielectric. And we've just seen that we know that lambda is equal to Vp over F. So if you replace Vp here with this Vp, you're going to end up with C over the root of ER times the frequency. And that's how you end up with this thing. That's how you end up with this thing over here. That's how you end up with this thing over here. C is a constant, the speed of light. And F, we're given in the question, is 1500 hertz. So if you make, this is supposed to be squared. So if you make ER relative epsilon r the subject, you get it is C divided by lambda F squared. So you just plug in your values of C, lambda, and F, and you get ER is equals to 30.86, approximately 30.86. Questions? Are we good? We're good until there.
Yeah.
So the last part is the line phase velocity. So Vp is equals to C over the root of ER. I think we have already seen that. We've just seen that. So you just plug in your values of Vp and your new value of ER. If you do the math with, again, with the calculator's value of this, not the rounded off value, you're going to get a Vp of 54 times 10 to the power 6 meters per second. And yeah, that is the end of this question. This question primarily covers up to, I think, section 2.5, which is wave propagation. The good news is that, well, with the exam being open book, you will need to cram any of these formulas. You can just open your book, jump in, find what you want, and then put it down on paper. Yeah. So, okay, what I can say for this part is as long as you understand, as long as you get this equation, again, like I said in the beginning, and you get what characteristic impedance is and how to obtain it, and the propagation coefficient gamma, you're basically set from up to section 2.5, which is wave propagation. As long as you know those three things, you're good. Now it's just a matter of a bunch of formulas taken at different frequencies, which again unaweza jiangalilia in case you forget. So yeah. Question 3 and sections 2.1 to 2.5 go. I'm still presenting. So
Okay.
I'm assuming there are no questions. We were shouting so much. Yes, I know. I'm sorry. I'm so sorry, everybody. It's been a long day. Alright, so Fiona will take us through part B.
I'll do my very best to I will fly over part B because Gishero has said what is needed. So I'll only just take 5 minutes max. Peter will probably stop me. Hey, stop.
No, I'm supposed to put my baby to bed.
You stop me when I go past 11:20. I promise. It's just 5. I don't want to start doing this tomorrow. I'm sure we have more transmission lines questions. Okay, so
Yeah. Okay.
So
Sawa.
I'm going to present my seems like Akileman. So I'm sharing my screen. When it's on, just let me know. Okay. So the question. Okay, very
Yeah,
good.
we can see
So the question is, a transmission line, I hope you can see, a transmission line has a resistance of 50 ohm per kilometer, inductance of 1 millihenry, capacitance of that, and a conductance of that. Determine the inductor loading required to achieve distortionless transmission and calculate the percentage change in phase velocity as a result of the loading. Okay, so there are two things here. When we read this question, we had no idea about this inductor loading and distortionless transmission. So, distortionless transmission, it happens when R over G is equal to L over C. And then so that's what happens for distortionless transmission. Beta varies directly with, the phase coefficient varies directly with omega. So this condition where it's lossless, it's called the Heaviside's condition for distortionless transmission. So I don't want to go through all that. All these are in his notes. Just go check page 69, page 73, and page 75. What else do we need to know here? We already know distortionless is R over G, when R over G is equal to L over C. So I will read this short part. For practical lines, R and G will be as small as possible the ratio. Okay, no, that's not the next line. One common form, oh wait, the ratio L over C will in general not equal R over G. This is very true. So, and in all practical cases, the equality is achieved by increasing L by a technique known as loading. And this is what the question is asking us. So one common form of loading is to add inductive coils in series with a line at regular spaced intervals. Complete distortionless transmission would, however, require an inordinately large value of inductance and is thus not practical. So you'll find large inductances also decrease phase velocity. So we're going to see all these things in the question. So yeah, so just check page 69, page 73, and page 75 for more information on distortionless transmission. But what you need to know is R over G should be equal to L over C for distortionless transmission. Yeah, so that's like Heaviside condition. Okay, something else about distortionless transmission, maybe something I should add on. I don't know, I'm not seeing a paper is like talked about it. We've seen the phase coefficient varies directly with omega and the phase velocity is constant. This is with respect to frequency. So you'll find this is not always the case generally. So you'll find for the non-sinusoidal waves that they're like traveling at different velocities. So there'll be different velocities. So if the phase coefficient isn't proportional to omega, there's dispersive transmission, and then we'll have something called the group velocity, which is delta omega over delta beta. So this is the velocity at which energy is propagated down the line. Are we good up to that? This just FYI because I wanted to cover everything on distortionless transmission. So when you find that beta varies rapidly with omega, dispersive line results. So it has a lot of distortion. So there are two conditions for distortionless transmission. So this is a formula. This is like the line equation. Beta is equal to that plus beta naught. That's beta is equal to TD omega plus beta naught, where beta naught should be equal to plus or minus n pi. And the second condition, TD, is equal to the reciprocal of, what did we call this thing? Group velocity. Yes. So you can see the gradient is this TD, the y-intercept is beta naught. Have I rushed through that, or Mumelewa, can you now do the question? Can we now do the question, guys?
Yes. We can do the question.
Okay, so the what does the question say? Okay, now we know. Now, okay, so we want to prove that let's see if this thing is distortionless or not. So what did we see? Can you guys see?
Yes.
Yes.
No.
Now we can't see.
Oh wait, no.
Oh yeah, thanks. To be a constant. TD must be a constant, yes.
Fiona.
Yeah?
We can't see your screen now. Oh, okay. Imefika.
Okay. So we know R over G should be equal to L over C. Sindio. And R over G, what's R over G? Gosh, did I calculate this thing? Yes. So we found when you did 50 over 2 microsiemens, kilometer itaenda, sindio, and this is ohm, is equal to, what is L? 1 millihenry over 0.05 microfarads. When you do this, you'll find they're not equal. So They're not equal. I wrote it down, I calculated, I saw that it wasn't equal. But you can try yourself and you'll see that it's not equal. So what do you do when you, okay, so it's not equal. So for us to do that inductive loading, we were told you need to add so that the impedance can, should I call it impedance match? Yes, so that they can match, the R over G can match L over C. So we'll say 50 divided by 2 microsiemens, 50 ohms, divided by 1 millihenry plus X. X is what we need to add, right? Is equal over 0.05 microfarads. Single. So when you do that, we say that, so we say this 1 microhenry plus X, we say this is equal to, we say that is equal to A, single. So A is equal to 50 times 0.05 micro, all this divided by 2 microsiemens. So A, you'll find A is equal to, when you do that, you find, when you punch that in, what you find? You find that is equal to 1.25 Henry per kilometer. Sawa. But it's not A what you're looking, A is not what you're looking for. We're looking for X. So this is equal to 1 microhenry, millihenry plus X. Sawa. Tuko pamoja hapo. So once you do that, yes, X is equal to, what is this algebra? X is equal to 1.25 minus 1 millihenry. Single. So 1.25 minus 1 millihenry. You get 1.249 Henry per kilometer. So that's our X. And that is the inductor loading required to achieve distortionless transmission. Remember that it is not A we are looking for. We are looking for the inductor loading required to achieve, because this was already there, the 1 millihenry was already there. So what do you need to add to that so that L can achieve distortion, so that the L over C can achieve the same impedance as on this other side? Am I saying impedance? Wait, so that it's R over G should be equal to L over C. Is there any question there? Okay. So calculate the percentage change in phase velocity as a result of the loading. And from the equations Gisheru was showing us, he took us through that, and we saw that phase velocity is equal to, phase velocity is equal to 1 over root LC, and we have L and C, but we have the L, and we have the old L, and we have the new L. So let us call this the old. So that when you punch in 1 millihenry times the capacitance 0.055 microfarads, and remember all this is in kilometers. I'll write it nicely and send to everyone. So when you do the old phase velocity, you get 1.41 times 10 to the power 8 meters per second. Then we do the same thing for the new phase velocity. It will be, not the new one, we're going to say what are we going to use for the new one? We're going to say 1.25 because now that's the new value for our inductance. 1.25 Henry per kilometer times 0.05 microfarads per kilometer. And when you do this, you get 4. Wait, you guys are not telling me I'm doing something wrong here. Wait. Oh yeah, here I remember I changed this kilometer to meters. So when I also change these kilometers down here from this square root place, this area here, I have to give my answer in meters per second because it's velocity. So it's 4 times 10 to the power 6 meters. What is this now? Meters per second. Okay, fine. So we have the old phase velocity and we have the new phase velocity. So to find the percentage change, we'll say VP old minus phase velocity new divided by VP old times 100, which is equal to, remember the new phase velocity, come on, notice, as you can see, the new phase velocity has reduced. The old one was times 10 to the power 8, and then the new one is times 10 to the power 6. And I don't know if you guys remember when we were reading somewhere here, large inductances also decrease phase velocity since the velocity is inversely proportional to the root of the inductance as seen earlier. And our inductance has changed from 1 millihenry to 1.25. So now, yes.
It's new minus old. It's new minus old.
What's new? New.
It's VP.
New.
It's VP new minus VP old.
VP new minus VP old. Okay. VP new minus VP old.
But VP old is larger.
Yes, VP old is larger, but you see, Fiona will explain. She's already explained it before when she said that inductor loading leads to decreasing phase velocity of the wave. So this will end up being a negative answer. The negative. So.
Yeah. Thank you. So decrease. So that, yes. Thank you very much. Now what are we gonna do? Okay. Let's just delete all of this crap. Delete. Why is it taking such a huge? Okay, got it. Okay, so thank you, Mr. G. So we're going to have VP new minus VP old divided by VP old times 100. So it's 4 times 10 to the power 6 meters per second minus 1.41 times 10 power 8 meters per second. Give the handwriting 1.41 times 10 to the power 8 meters per second. And then times 100. So we are going to get negative 97.16%. So determine inductor loading required to achieve distortionless transmission X, and we found X as 1.249 millihenry, and calculate the percentage change in phase velocity as a result of the loading. So I think so percentage change. So our answer 97.16 change, and this is sorry, this is a decrease. Thank you, everyone. Okay, how do we stop presenting? Yes.
Oh, okay. Thank you.
I'm done.
Thank you, Gishiru and Mona. So, Nigel is going to present tomorrow. So I'm going to stop recording so that we can discuss what you're going to do for machines.